Hey everyone, this is Derek, and in this video we're going to look at something called the chain rule, and we're going to see two forms of it. We'll do form 1 in this video, form 2 in the next video. And what the chain rule does is it allows us to take the derivatives of composite functions. And so you might remember, hopefully you remember from earlier in the quarter, we had f of g of x when we did the function review at the beginning. So this was a composite function, and this is where one function was sort of nested inside another function. So an example of that would be something like x plus 2 to the 7th. So the inside function, the g of x is the x plus 2. The outside function would be like a x to the 7th. So this form, that's what the chain rule is going to do for us. So we got two versions, and so in this video we'll look at form 1. And I think it's easier to follow the notation if I point an example, so I'm going to kind of bounce back and forth between these. So if y is a differentiable function of u, so here's an example, we have y equals 3u, so I could take the derivative of y with respect to u on that. And then u is a differentiable function of x, okay, so there's that one, because I could do du, and then that would be dx on this side. Then the derivative of y with respect to x, so that's y with respect to x way over here, is going to be the derivative of this one times the derivative of that one. So that's what this is saying. So essentially we just have to take the derivative of each of these and multiply them together. And where the composite piece comes in on this is, notice if I wrote this, and I'm not going to do this in this example because kind of form 1 is for when they are separate. I kind of like form 2 better for when they're not, so I'll show you that one coming up in a separate video. But where the composite piece of this is if I substituted, so u is x squared minus 5, I could put that right here, and then that would make this y equals 3 x squared minus 5 plus 7, which I could then do some work on. But that's where the composite is coming in. But in this case, they're not showing it to us as a composite. They're showing it to us as two separate functions. So that's where we use form 1. Okay, so we're supposed to find the derivative of y with respect to x. So the first thing here I need is dy du. So here is my my y, and so my dy du, my derivative of y with respect to u, is just 3. And then we'll do the same thing over here. We need du dx, so u is x squared minus 5. So du dx is 2x. And now dy dx equals dy du, so that's right here, that's the 3, times du dx, so that's this one, that's the 2x, so that would be 6x. Okay, one more example in this form, and then the second form is really kind of more the workhorse of the section. It's the one that you'll probably end up using the most. So for this, we're going to do the same thing. I have my y right here, so I'm going to go y equals 2u squared minus 1. So then dy du equals 2 times 2 would make 4u, take 1 off. And then u is 2x squared plus 3. And then du dx, u with respect to x, 2 times 2 is 4x, and then take 1 off. So then remember from the last page, we multiply these two together, and then that gets us our dy dx. So dy dx is going to equal 4u times 4x. Okay, so you can see there's a little problem with this one. So 4 times 4, that would be 16. So let me write that as 16xu. This still has a u in it, and we're supposed to be taking the derivative of y with respect to x, and there's still this u floating around. So that is problematic because I can't have both variables, but we're cool because up here we know that we know u in terms of x. So now I can do that little substitution, and now I'll have the derivative of y with respect to x alone. So we'll just substitute that in for u and then distribute, and we got it. So what we got, 32x cubed and then 48, oops, 48x.